Hi folks, my name is Mickey Rowell, and I'll be your presenter for this video tutorial on Sheffield roughness. Thanks for watching. I think many of you out there watching this video will recognize these tools here. What I'd like to do today to kind of give you a little bit of background on actually what's happening with this particular method, and a little bit about where it came from. These folks, the Sheffield Corporation, actually developed this tool, I would say in the early to mid 1950s. They were already quite heavily involved in designing of rotometer tubes for other measurement systems. A lot of air leak tests, certainly using for different flow measurement systems. Also, again, dating back to some of this testing that the automotive and machining industry got involved with. I discussed this technique quite some time ago in an earlier video, but they took that technology, what they knew about flow rotometer tubes, and then incorporated all those pieces together to build this tool that they can use for roughness, surface roughness testing. Their design happened to be, let's say, have some assistance, I guess I would say, from their predecessors, because we're talking about some early developments in the 1930s into the late 1930s, early 40s. I think these people had a little bit of an edge in that they saw some of the good and bad of the methods that were done prior to the development of this tool. All right, we stepped out of our studio just for a moment so I can go in, dive a little bit deeper into the design of the measurement head and the backing that was selected for this particular test. In an earlier video, I discussed the idea of if we had a single annular ring device like our Benston head, I invert that onto a sample. If I can charge that cavity inside, really the only reason that I'm going to see some leakage underneath here is due to the topography of the paper sample itself. Now, when we start looking at the Sheffield measurement head, this is more or less a completed assembly. The design is slightly different. We have two annular rings. They're concentric. The surfaces are lapped optically flat. The backing that was selected was a glass backing. That is also lapped optically flat, so that when I invert this measurement head just on the glass backing itself, that's my starting point, and I should essentially get zero airflow. Okay? When the when I'm interested in taking the measurement, now I'll place my sample piece of paper on top of the backing, put my measurement head in place, have my weight, of course, on the measurement head. I'm going to charge in between those two annular rings with this fitting right here. This source is going to charge in between these two annular rings. Now, because of the undulations in the paper, I'm going to get air leakage from the outer ring to atmosphere, from the inner ring also going to atmosphere. We have a hole that's built into the design of the measurement head that allows it to leak out in that direction. So, all right, so we're going to pressurize the area that's underneath these two annular rings. This area here, of course, this is a cut view. And once we do that, of course, we have the weight of our measurement head resting on top of our sample, which is resting on top of the glass plate. The only path that this air really has to go is out underneath the annulus, over the top of the surface of our sample, and leak to atmosphere. This image is a little bit misleading in the sense that we have a path. There have always been a path that has been opened up here right in the center of the two annular rings that will also allow this air to pass and go in this direction to atmosphere. So we have a lot of pathways. We have a fairly large area that we're testing the sample surface with. If we can, if we can regulate the air pressure going to this area, this annular area, we can regulate that to a fixed pressure drop. We then get a good indication, a good smooth flow of air, and we can measure with a device similar to this. This is going to give us a scale in terms of Sheffield units. I don't really know the history of the Sheffield unit. I think originally they thought it might have been some type of engineering unit. That doesn't turn out to be the case as we've studied this more and more as time went on. So also the original design of this tool was, again, to create a scenario where we can have a measurement value, a target measurement value that we can quantify, that we can say, yes, this is acceptable to our customer. We designed this full range from 0 to 300 Sheffield units, and we break it up, that range, that working range, up into 3 different rotometer tubes. First rotometer tube being roughly from 0 to 60 Sheffield units, second tube being roughly 60 to 180 Sheffield units. The last one being set up here will provide us an opportunity to reach 180 to 400 Sheffield units. So as we are starting our production process in the mill, our products are going to evolve. They're going to have different surface characteristics, and we might actually go from a Xerox type paper to a heavily coated paper. I doubt in the same mill that we'll see something with as much corrugation as this, but it gives us an opportunity to be able to use this tool in a number of different settings. If we put a sample similar to this, glossy coated grade, underneath here, we're going to get a pretty low flow out from underneath these annular rings, and if we had one single measurement device, it might be way on the low end of that measurement device, and the resolution at that flow rate may not be accurate enough for us to be able to distinguish from one run to another. So if we broke it up like the Sheffield Corporation did, we use this first gauge, and this runs from 0 to 60. A product like this may be somewhere around 25 or 30 Sheffield units, okay? So another day I might be running a product that might be similar to this. I put this down on top of my sample, start my test mechanism, and I might be reaching somewhere around 100 Sheffield units. Well, you can see that the scale and my first gauge is out of range. I need to toggle to my second gauge. Now I can get a pretty reasonable number, 100 Sheffield units. That's pretty close to the center of my working range of this flow meter. That's a reasonable place to be measuring it. So if I take this tool and I bring it to yet a third manufacturer, I start to measure something of this product. Now all of a sudden, now I'm reaching or maybe even exceeding the 400 Sheffield unit range. However, if I am, let's say, at 300, 325 Sheffield units, I can use this last range and still get a good, reasonable reading off of my system. So I want to reproduce this tool. The original manufacturers of this tool really didn't have in mind the desire. I'm not sure how this particular mindset came about, but really the original design was to be brought to a mill system, and you set up a relative target for your products in that particular mill system. You take another unit, you bring it to another mill, and you set up another target for that particular product. They may be similar products, but because they didn't design this tool to be able to be transferred from one mill to the other and get the same results, now we have this early, let's say that this early family of instruments that are out in the field that are if I'm trying to compare from one mill to another, which is a common occurrence today especially, maybe not so much in the 50s, but if I'm trying to compare one mill results or my customer is trying to compare the results of my sample versus another competitor, now they have some trouble actually looking at these two results. One might say 175 Sheffield units. Another one might come back and say 125 Sheffield units. So which one is better? In actuality, they both could be the same, but because of the, let's say, the inconsistencies in the design, the original design of the system, you couldn't tell that from just reading the results off of the system. So in any case, later on in the development or usage of this tool, we began to use mass flow meters, and we were able to convert these scales, these three scales, to engineering units, milliliters per minute. We can repeat those numbers quite well. We can build a whole family of these instruments that'll read the same in a reasonable fashion, and be able to share my results. Let's say I can share my results to my customer. My customer can look at those results, and he can look at results from another competitor or another supplier and have a reasonable understanding that those two products are probably going to be the same. My image is going to work well, and our production is going to continue on for that day. Later developments were an effort to bring these family of instruments in better reading, let's say, reproducible form, and now we have what we look at today as a pretty reliable instrument. This design here, again, if you're looking at trying to repeat this design, build a family of instruments or specific details that you need to pay close attention to. One certainly is the backing, the glass backing for Sheffield. The test area, again, these annular rings are precision ground, precision made. The dimension, the width of these annular rings need to be remain the same, and the loading pressure. This again was 1,640 grams, I think. If I have 1,200 grams and I try to use this weight, compare it to this weight, my numbers are going to be different because the forces that are put upon the sample to sandwich it in between the glass plate and my measurement head are going to be different. So I'm going to either allow more air to escape or less air to escape. Now I can't compare this unit to this unit as an example. So that's it in a nutshell. Hopefully you've gotten a little bit more information as we continue on with our series. So I appreciated your stopping by and watching this. Please come back and look at, if you haven't already, look at the other series that we've created, and we'll continue on with the next method in our list. After watching this video, you should have a good foundation of moving forward in the series. Like always, we enjoy helping our customers. If you have any questions, please don't hesitate to contact us because our goal is to help you make better paper.